Hi, I'm Elad. I'm the founder and CEO of NextSilicon. Today I want to share what we are doing at NextSilicon. We have invented a radical new compute architecture, purpose-built and original. It combines software intelligence and hardware flexibility in a completely new way. Unlike others who are just focused on solving the hardware problem, we take a complete system approach. For the first time, we are bringing together hardware and software, a dataflow processor with a smart software algorithm, a new compute platform for the next-gen AI and HPC. Our dataflow allows your data to drive your application and optimize your software, not the other way around. We have seen that for compute-intensive applications, a small portion of the code, a tiny bit, runs the majority of the time. We have decided to take it to our advantage. Instead of running every piece of code, every instruction the same way, we thought, let's focus on what matters. We developed a smart software algorithm that continuously monitors your application. It identifies precisely which code path runs the most, and it reconfigures the hardware on the chip to accelerate exactly those code paths. And we do this all at runtime in nanoseconds. The result? Efficient performance at scale for the most critical workloads, freeing you to focus on innovation, not overhead. NextSilicon is redefining computing by creating an entirely new generation of compute infrastructure. Our technology seamlessly runs CPU and GPU code, supercomputing tasks, HPC workloads, and advanced AI machine learning models, all effortlessly, out of the box, and as a drop-in replacement. This means no vendor lock-in. Our customers can spend more time doing what they love instead of code rewrites and porting. At NextSilicon, we are reimagining what computing can be, where hardware finally bends to the needs of software, not the other way around. Just as GPUs once displaced CPUs, our architecture is poised to redefine compute all over again. Today, I will show you exactly why. I'm proud to introduce the first intelligence compute architecture. It's a complete reimagining on how hardware and software interact. Our architecture moves beyond the limitations of traditional approaches that force customers to rewrite software and adapt to the rigid hardware constraints. So how does it all work? Our intelligent compute architecture is based on the Pareto principle, the 80-20 rule. And in massive parallel code, it's even more extreme. 1% of the code runs 99% of the time. Our sophisticated software algorithm understands what's happening in the application. ICA identifies those critical hot paths in real time. It reconfigures the chip to accelerate exactly those parts that matter now. It gives them more transistors, more compute, and more love at runtime. The result? A software-defined acceleration that will improve performance over time. We get 10x faster performance at half of the power consumption, and because we are a drop-in replacement, we can penetrate the market much more quickly. The Maverick ICA can deliver immediate performance with zero porting risk. We don't offer just a performance or efficiency improvement. We are offering a completely new way of how performance can be delivered. To conclude, we are building the chip of the future. A universal chip, better performance and greater efficiency. Our ultra-flexible design is engineered to be future-proof, delivering market-leading performance no matter how science and AI models evolve. And it does so as a true drop-in replacement. No rewrites, no vendor lock-in, no long, costly porting cycles. Just scalable performance ready for the future of humanity. Maverick isn't just built for the future, it's built to define it. Join us in shaping a new era of compute, where the possibilities are limitless. I would like to welcome on stage Eyal Nagar, my co-founder and EVP of Engineering at NextSilicon.
Hello everyone, I'm Eyal Nagar, co-founder and VP R&D at NextSilicon. It's an honor to stand here, not just to unveil our Maverick-2 product, but to introduce what we believe is a new era in compute. Today, I'm proud to introduce Maverick-2, our next-generation compute accelerator, which is already running at customer sites and showing remarkable performance. Using its intelligent compute architecture, Maverick-2 delivers performance, efficiency, and scalability as it plugs directly into your system. Maverick comes in a PCIe card, full-height, double-width form factor, and it's powered by our massively parallel dataflow grid. We also offer an OEM form factor version, designed for efficient compute at scale for higher density. This isn't just a chip, it's a complete reimagining of how hardware behaves. Let's start with a single die version. It's built on TSMC 5nm process. It runs at 1.5 GHz and supports PCIe Gen 5x16 for maximum host connectivity. On chip, it features 96 GB of HBM3 memory, delivering a massive bandwidth of 3.2 TB per second. Maverick features a remarkable 128 MB of L1 cache system designed specifically for HPC and AI workloads. Smart, on-chip, and optimized for sustained throughput. Now, your most demanding workloads will stay close to the compute engines where they can run at top speed. We also included a 100 gigabit Ethernet link for node-to-node interconnect. The TDP for this card is 400 watts, and we offer both air and liquid cooling options for flexible deployment. Now let's scale it up to our dual die. This version uses an OCP accelerator module or OEM form factor, and as you can see, the data flow performance doubles along with everything else. HBM memory is as high as 192 GB with enormous bandwidth of 6.4 TB per second. The TDP also doubles up to 750 watts. In real applications, we are seeing utilization that's lower than that, so performance per watt is exceptional. You might be wondering why we use HBM. High bandwidth memory is critical for HPC and AI. It provides enormous data throughput directly next to the compute engines, reducing latency, power, and bottlenecks which slows down the application. We have only just begun to fully optimize the hardware and software stack, and we are already delivering breakthrough performance that surpasses existing solutions. I eagerly wait to see what innovations our team and partners unlock in the years ahead. And I couldn't be more proud of the incredible team that made it all real. Thank you.
I would like to welcome on stage Ilan Tayari, my co-founder and VP Architecture at NextSilicon.
Hello everyone, my name is Ilan Tayari. I'm the VP of Architecture and a co-founder at NextSilicon. In my 30 years of work, software and hardware architecture have been a central part of my life. Over the years, I developed the ambition to revolutionize the way we design chips and systems for performance. Founding NextSilicon allowed me to realize this vision. Today's GPUs and CPUs struggle to perfectly execute parallel applications at scale due to their inherent design characteristics. These traditional designs of instruction set processors are based on the von Neumann architecture, first introduced over 8 decades ago in the 1940s. Instead of trying to patch this 80-year-old model with sophisticated workarounds, we needed to embrace a new one. What if we could dedicate the majority of the area to ALUs, the units that actually perform computations? A chip like that would have the potential to get 10 times the performance at a quarter of the power consumption. That brings us to a data flow architecture. In direct contrast to von Neumann, data flow is a data-driven paradigm, where the data drives the program and the optimizations on the hardware, not the other way around. The main unit is a compute block, made almost exclusively of hundreds of interconnected ALUs. Each ALU is analogous to a compute instruction. Each ALU is configured to perform a specific operation: addition, multiplication, bitwise logic, bit shifting, and so on. The main unit is attached to a memory bus to receive data. Let's go one step further and see how compute programs map to this. To understand how a function runs on the dataflow architecture, let's look at the code sample of a reverse function. This is a bit reverse function for 32-bit integer. The compiler builds an intermediate representation graph for it. A CPU compiler takes this graph, turns it into registers and instructions, and then encodes them into machine code. Compiling to a dataflow processor is different and a little simpler. The compiler maps each graph operation to a hardware element, an ALU, in a process called projection. The graph is projected onto the dataflow processing grid. No more register assignment, no more instruction scheduling. Instead, the compiler generates configurations for hardware elements and their dataflow, similar to machine code. The resulting entity is what we call a mill core. It is a software-defined hardware. An application-specific processing core optimized for a particular application. During compilation, your code is transformed into a fat binary with two parts. One part is native for the host CPU, and the other is intermediate representation. At runtime, our system takes over. It identifies the hotspots and the potential bottlenecks in your most likely code paths, all from the intermediate representation. It creates the mills and projects them onto the Maverick dataflow grid. The rest of the code continues running seamlessly on the host CPU. But we don't stop there. This is where the intelligent part of our architecture truly shines. Maverick uses live telemetry to constantly optimize the application. This is what we call runtime optimization. For example, if two mills communicate frequently, they will physically relocate closer together on the chip to reduce latency. If there is a bottleneck, the mill duplicates to increase throughput. These optimizations happen dynamically with zero developer input. This is more than just optimization, it's evolution at the speed of runtime. And because our system is also AI stack agnostic, it works across the full range of modern machine learning tools and frameworks, from TensorFlow, JAX, PyTorch, or Onyx, and anything you'll find on Hugging Face, including specialized custom MLOps written in CUDA or Triton. You don't need to modify your application to get acceleration. Our architecture learns your workload and adapts to it, not the other way around. Remember CNN-specific accelerators? They're paperweights now, useless for today's transformers. This is the ASIC trap. Optimized for today's models, become obsolete tomorrow. Just as GPUs once displaced CPUs, our architecture is poised to redefine compute all over again. And it's right around the corner. I invite you to use it to shape your future too. Thank you.
We have spent the past 7 years building a chip of the future, and now we have the opportunity to reveal our results. Let me show you how Maverick-2 delivers on our promises. When you build a new chip, the first test everyone runs is Stream. Whether it's a CPU, GPU, or a new architecture. Stream is the industry standard starting point. And companies invest a lot to tune Stream for their systems. For us, full scaling of our HBM, right out of the box. No tuning, no custom optimization. This isn't just a benchmark victory. This gives developers confidence, performance that translates directly to the real applications. No surprises, no disappointments, just faster results from day one. Stream proved our memory subsystem delivers. Now let's stress it with real chaos. Gaps is where most architectures have failed, and it's where our ICA stands out. Let me tell you what Gaps is, and why it broke every existing architecture. Gaps is messy, it is unpredictable, it stresses a system with random memory access patterns. That randomness is exactly what makes it so challenging. Maverick-2 delivers 32.6 GOPS at just 460 watts of total power consumption. Here is the remarkable part. Our team achieved this using completely unmodified code, out-of-the-box code. Moving to more complex workloads. HPCG is the gold standard benchmark for HPC. Win HPCG and you won science. Maverick-2 delivers 600 gigaflops at 750 watts. Out of the box, we are beating the performance of the most widely deployed GPUs in the industry, at half the power with zero code changes. Let me repeat that. Better performance, half the power, zero code changes. Imagine the potential when scaled to many devices at the system, rack, and data center level. You won't have to wait long. More details on our performance at scale coming soon, to be announced with our customer, Sandia National Laboratory. Stay tuned. Now, let's look at graph analytics. Using PageRank, the algorithm that started at Google to rank billions of pages. Maverick-2, 40 giga pages per second, a whopping 10x performance over leading GPUs at half the power. Today, you have seen that vision become reality. Across GAPS, HPCG, Stream, PageRank, and more, breakthrough numbers at a fraction of the power, delivered through software-defined intelligence that adapts to your applications, not the other way around. The future of computing isn't just faster, it's smarter, it's more efficient. It's here. Maverick is here, and we are just getting started. I want to show you one more thing. This is the Maverick-2. And today, I'm proud to introduce Maverick's little test brother, the Arbel. Every application has two fundamental parts. There is massive parallel code that our dataflow grid handles, and there is serial code that needs to execute with low latency in a CPU core. So we built our own RISC-V cores. Those cores performed so well that we started thinking, what could be possible if we test it with a dedicated chip? The result is what you are about to see. Here is the Arbel, a new enterprise-grade RISC-V performance core. We have built a massive instruction pipeline. It has a 10 wide issue width with a 480 entries in the reorder buffer. This is our own patent IP, not licensed, not borrowed, built by NextSilicon engineers for NextSilicon vision of the future. Here is something I can tell you. We are crushing the current RISC-V competition, and we are standing toe-to-toe with Intel Lion Core and AMD Zen 5. This is not a catch-up core. This is a leap ahead core. So that is our one more thing for today. Not just the industry's most advanced dataflow accelerator, not just another RISC-V announcement, but proof that NextSilicon doesn't just talk about innovation. We build it from the ground up, in silicon. While others share their plans, we are sharing our results. Thank you for joining us today, and stay tuned. We are just getting started.